Right, inverse functions. So this is probably something that you're at least a little bit familiar with from high school, and maybe you already know everything that I'm going to say about this. But I want to talk maybe a bit more like technical details about inverse functions. So the idea behind this is when f of x is a function, sometimes we can talk about the inverse function. We can talk about, we write it this way, f inverse of x, the inverse function. Right? This is something that's slightly confusing. Maybe this little -1 up here, it does not mean 1 over. As when you write a power of -1, that's the same as 1 over, like x to the power -1 is the same as 1 over x. But in this context, this is not supposed to be interpreted as a power -1. It's supposed to just mean something else. It means the inverse function. So let me just say, this is not the same as 1 over f of x. All right, it's something else. It's the inverse function. And what it means is, so f inverse of x is the function that sort of, I'll kind of put this in quotes, like does the opposite of x, of f. Does the opposite of f of x, or maybe cancels f of x, right? That's the meaning of f inverse of x. For example, like if f of x equals x cubed, then f inverse of x is, so this is another function which does the opposite, or cancels, or like undoes whatever the first one does. The first one is cubing the number. Can anybody say what's the inverse of that? That would be the cube root. Yeah. So this is cube root of x. All right. That's the inverse of cubing. All right. I will just say again parenthetically, it's not x to the -3. Although I don't know. Just looking at those, you might think, oh yeah, that's like, this is like the opposite of that. Although it's not. At least not in the sense that I'm talking about. The proper inverse of the cubing is the cube root. If you wanted to write it as a power, this is x to the 1/3 power, not x to the -3 power. All right. This is the inverse. Like, why is it the inverse? It's the inverse. What I mean by this, like canceling or undoing, it's the inverse because if I start with x and I do the cube and then I do the cube root, I end up with x again. That is, these two operations, when you do one of them followed by the other one of them inside of the other one, they cancel out and you end up with what you started with, which is just x. So that has to be true, and actually, technically, it also needs to work the other way around. So it's also true that if I did the cube root first and then the cube, this also equals x. All right? And actually, this will suggest sort of the true definition of the inverse. We say that f inverse of x is the inverse of f of x. This is the real definition. This means that f of f inverse of x equals x, and f inverse of f of x equals x. This is technically what I mean when I say the two things cancel each other out, or one of them undoes the other one, something like that. It means when you stick them one inside of the other and apply that to x, you end up with x again. All right, this is what it means to be the inverse of something else. All right, these come up often in the real world. So often people talk about inverses of functions. Like here's a made-up example. How about if f of t equals how tall I am in year t. So t is like time. As time goes on, my height changes. These days it's not really changing that much, but for you all maybe it is. I don't know. how tall I am in year T. Can anyone explain in words, what does the inverse function of this represent? So this function is, I give you a T, which is like a time, and then the answer is a height. The inverse should be the other way around. Can anyone explain in words what that would represent? Yeah?
Like if you have a height, it tells you how old you are?
Yes, this is the other way around. If somebody tells you the height, the inverse will tell you what year it is, or how old you are, or however you want to say that. So F inverse would be the opposite. And in the real world, usually people like to use a different variable for this. So maybe I'll say H for height. And T is for time, of course. F inverse of H, what that means is which year it is when I have height H. That's the inverse function. It's the other way around, all right? Or how about here's another real world example. If, did you know I'm sort of as a side hobby of mine, I'm like a Z-list YouTuber. I make YouTube videos, it's true. If, let's say f of x is how much money I get, if my video has X views. I just had a video that sort of went viral last week. The cash is rolling in, my friends. It's not that much. What would the inverse function be? I mean, like the meaning of the inverse. This is, so here apparently the X represents how many views I'm getting, right? And then the answer here is the money. So it might be helpful to think in terms of the units. It should be the other way around. Yeah?
How many views you would get if you had X money?
Yeah, right. If you tell me how much money, then the inverse function will be how many views does it take to make that much money, right? So this one, the way this goes, it could be something like f of 1,000,000 views is $100. And the inverse would say f of $100 is 1,000,000 views, meaning in order to get $100, you have to get 1,000,000 views. So the inverse here, and I'll use a different, how about, I don't know, D for dollar. This would be how many views it takes to make D dollars. All right. And both of these things are interesting in the real world. That's all I'm saying, right? Actually, when I mention to people that I make YouTube videos, they often ask me both of these questions. Oh, how much money do you get for those? Or they might ask me, how many views would you have to get to make $100 or whatever? So one of those questions is about this, one is about the inverse. They are kind of both asking about the same thing, but it's just whether you say it sort of in one direction or the other direction. So these are important things in real life. Being comfortable with functions and the inverse functions. All right, yes?
Does the inverse of functions always have two variables that you're talking about? Like for this one it's x and d?
Yeah, it doesn't have to. I mean, as always, like in a mathematical function, you can call the variable whatever you want. So I could have called it x both times.
Okay.
I think it's in real life, it's usually clearer if you use different variables just because they represent different kinds of things. Here the x represents views and the other one represents the dollars. So it's kind of like using x and y in equations. You could call things generally whatever you want, but yeah, unfortunately this is something that will get confusing from time to time when we talk about these things. Anyway, this is easy enough on a chart of values. On a chart of values, for example, I could have one function. You know, some functions are just described by like charts of data. These are not, we usually don't talk about functions like this in a calculus class, but in real life, actually, these functions are extremely common, because things in real life usually are not described using equations. They're described just using a bunch of data. But anyway, here's a function described using a chart of data. If I plug in various values for x, you get various answers back. Can we give a chart for the inverse? So the inverse. Here I'm going to use the same variable name again, although you could call it something, you could call it y instead if you prefer. But anyway, what does the inverse represent? It represents kind of the same relationship, but just said in the other way around. So here, when x is 1, f of x is 6. What that means is when x is 6, the inverse is 1. It's just the same thing, the same relationship, but it's going the other way around. So this will be 6 and 1, 2 and 2, 1 and 3, 5 and 4, 0 and 5, right? That's the inverse function. Here I use the same variable name in the inverse as the original function, which is fine. You can call the variable name whatever you want. All right. One thing to notice, though, in this approach, there will be a problem. There's a problem if two values of f of x are equal. I think you'll see right away what the issue is. If two values of f of x are equal, for example, if I have, I'll write this as a little chart again. 1 and 3, 2 and 0, 3 and 3, 4 and 2. This is what I meant by two values. By values, I mean like the answers. And here you can see there's 3 appears twice in the list. Now, this is not a problem as far as the function goes. This is a perfectly legal function. But actually, this is a problem when you start to talk about the inverse. So then, f inverse looks like, well, it's written the same data values, but just written the other way around. So this would be 3 and 1, 0 and 2, 3 and 3, 2 and 4. I just swapped the answers with the x's. And can anybody say what's the problem here? I said there's a problem. Actually, the problem is not on the left side. There's nothing wrong with the original function f of x. There is something wrong with this other thing over here. Yeah?
It's not a function.
Yeah, it is not a function. Why not?
That's the bird walk test.
It's one of those line tests. Yeah, although this being, it's not, it doesn't really have a normal looking graph. I would say this is not a function because I have one x value here. 3, the x value 3 has 2 different answers in this alleged thing, which is not allowed for a function. A function means that when you plug one value in, you get one answer, not 2 different answers. So here, f inverse is not a function. And this is, you can still talk, it's still something, but it's not a function. So we generally don't want to talk about it, at least in a calculus class. We are concerned with functions. F inverse is not a function because f inverse of 3 seems to have 2 different values. The first row says f inverse of 3 is 1, but the third row there says f inverse of 3 is 3. All right. Sure. All right, so what that means is if we want to talk about, this is why I don't know if anybody thought it was weird. The very first thing that I said about this is when f is a function, sometimes we can talk about the inverse function, but not always. What is required? This kind of a thing is not allowed if you want to talk about the inverse. So to do, I'll say for f inverse to be a function, the values, let me say the y values of f of x must never be repeated. That was the problem. if you get the same y value twice, then then that's okay for a function to do that, but in that case you cannot do the inverse function. All right. There's a word for this. The y values of f of x must never be repeated. The word for that is f of x must be 1-to-1. That's the name for that. It means that your function never repeats any of its y values. Actually, this is not a very useful as a technical definition, so I'm going to give a fancier way of saying the same thing that I just said here. It is, what does it mean to be 1-to-1? F of x is 1-to-1 when, I'll say if, I'm giving you the definition of what it means to be 1-to-1. If f of, let's say, x1 is always different from f of x2, that is, any two different x values you choose, the y values are always different. This is what I mean. Above I said the same thing informally. It must never be repeated. The y values are never repeated. I should say something about if this is true whenever x1 is not equal to x2. Certainly, like if these x1 and x2 are equal, then these are automatically equal. But I'm saying when you have two different domain points and you plug them into the function, the answers you get are two different y values. That's what 1-to-1 means. All right? And this is something that is easy to look at, or let me just reiterate why we care about this. F inverse is a function only when f itself is 1-to-1. All right, that's why it's important for anything. And this condition about being 1-to-1 is easy enough to tell when you're looking at a graph. You can tell by looking at a graph if it's 1-to-1 or not. I'll draw two examples. One of these is 1-to-1 and one of them is not 1-to-1. How about this one? That's one, or this one here? Can anybody say the one on the left or the right? Which one is 1-to-1? Yeah, the one on the left is 1-to-1 because it never repeats any y values. You can see here these y values are always different as you move along the curve. Versus this one over here, actually it does repeat. For instance, this y value occurs over here, but it also occurs over here. And so this one on the left, this is 1-to-1. And this one is not 1-to-1. Because, for example, like this y value here also exists here on the same curve. And they are, they line up. Another way that people talk about this is in terms of what they call the horizontal line test. In order to be a function, it has to satisfy the vertical line test, which means any vertical line must hit only one point. And that's true of both of these. Any vertical line hits only one point of the graph. But the 1-to-1 business is about horizontal lines. So this one is 1-to-1 because any horizontal line touches the graph once. Whereas this one is not 1-to-1 because some horizontal lines touch the graph more than once. Although this one right there only hits it once, that's not good enough. There are others which do not. All right, that's called the horizontal line test. All right, great. This is a bunch of sort of random facts about inverse functions, which will be tied together eventually, although at this point, unfortunately, they are kind of somewhat random facts. It can be difficult when I just show you an equation to tell if it's 1-to-1 or not, but in some cases you can. Even without looking at the graph, I would say, for example, even without looking at the graph, f of x equal x squared is not 1-to-1. Now, if you imagine the graph, you can tell that any horizontal lines will hit 2 points on the graph. But rather than looking at the graph, we can also do this in terms of the definition. This is not 1-to-1 because, using the definition, remember this is the true definition. It's just that two different x values will always give you two different y values. Can anybody suggest that the f of x equal x squared actually doesn't satisfy this. What that would involve would be, all you have to do is explain, is it actually possible to fill in the blanks with two different x values, but the y values are the same? That's what I'm looking for. Can anybody suggest? Yeah? 2 and negative 2, yeah. I was absolutely sure somebody would say 1 and negative 1. She ruined it. She said 2 and negative 2. It's a perfectly fine answer. Yes, because f of 2 equals f of negative 2, and the answer is 4, right? So that means, well, I was going to say it again. I guess I don't really need to say it again, but f is not 1-to-1. This is like using the actual definition of 1-to-1 rather than talking about pictures and line, the horizontal line test or whatever, which is totally fine on an intuitive level. It's not very satisfying to sort of prove something conclusively just because you have to draw a picture and draw a line and whatever. But this is a very clear explanation as to why x squared is not 1-to-1. All right. A few more kind of random facts about. I don't want to say those random facts. How about finding the inverse of a function? This is what we can talk a little bit about, and this is something that I'm sure you've all done in high school, so we can just do this real quick. Sometimes we can find a formula for the inverse. Sometimes, this actually is not always possible to do, but sometimes we can find a formula for f inverse of x. For example, how about find f inverse of x for f of x equals x cubed plus 2, all right? And there are a few different ways that people sort of learn how to do this. But the usual way, I mean, any of these ways will involve writing something like y equals x cubed plus 2. And then I would say you want to make a function which is the opposite of this. This function takes a x and gives you a y. What I'm going to do is solve this formula here for x in terms of y. That's because I want to write this as a function going the other way around. So I'm going to solve for x in terms of y. All right. Can we do that? I think we can. I would subtract the 2 from both sides and then take a cube root on both sides. So it would say, subtracting 2 first, x cubed equals y minus 2. And then we can solve for x by doing the cube root on both sides. X equals cube root y minus 2. And this is the inverse function now. That right there is the inverse function. You could write it this way. F inverse of y equals cube root of y minus 2. Or if you prefer, some people like to use the variable x for everything. And as I've said before, you can call the variable whatever you want. So if you like, you could write it this way. F inverse of x equals cube root x minus 2. All right? To me, I kind of prefer writing the inverse the first way. I'll put a little smiley. I like that a little bit better, just because to me what the inverse means, like the variable that you use in the inverse, means something different from the original variable, at least in most sort of real-world settings. The meaning of this variable that you're plugging in here is different from the meaning of this variable that you're plugging in here. So I kind of prefer to leave it at that, although some people really don't like to use variables that aren't called x, or maybe t. On a good day, they will allow a t. But this, in that case, I mean, if you want to use x, that's totally fine. Some people, when they learn this in high school, they say the first step is to interchange the x and the y, and then you solve for y again. This always struck me as kind of weird, but if you want to do it that way, that's fine with me. All right. Any thoughts about that one? I said sometimes you can do this. Sometimes it just straight up doesn't work, though. For example, here is, I will just say this doesn't always work. Let's try something like f of x equals x cubed minus x plus 2. Find f inverse of x, or f inverse of y, whatever. Find the inverse function. So I would start by writing y equals x cubed minus x plus 2. And then the next step would be to try to solve this for x in terms of y. Anybody got an idea for that? Yeah?
Complete the square.
Complete the square. I was going to say, I don't know what to do. This is a cube. If that were a square, you could complete the square.
I remember learning something like that.
Yes. If this were a square, you could complete the square and do some business with some square roots. I mean, if that were a square, then it's not one-to-one, so I wouldn't even be trying to do this. But yeah. This is good. There are very specialized tricks which are sometimes necessary in order to solve things like this. Completing the square is one which works for squares. But in this situation, actually, I am not aware of a way to solve this for x. You could, I mean, in the worst case, you might think of subtracting the 2 and then factoring over here. But this is not going anywhere, really. You're not going to be able to just solve for x by itself in terms of y. So all I'm saying is sometimes you just can't solve for x.
Would you ever give us one and then like the answer is you can't do it?
No. I would, no. I definitely wouldn't say do it if the answer is I can't do it. I might say do it or say that you can't do it. And then you say I can't do it. Yeah. But I wouldn't tell you to do something if I know that it's impossible. Yeah. I had to be careful about the language. I once put on a test something like answer this question or say that you can't do it. And somebody said I can't do it when actually they could. And I marked it wrong. And then he came to me afterwards. He's like, I didn't know how to do it. So I said I can't do it.
Did you give him the points back?
That's not what I meant. No, I didn't. He knew that I wasn't going to go for it, and I didn't. All right. A few more random facts, and then we'll talk about something that maybe you haven't seen before, although maybe you have. One last thing is about the inverse on a graph. So if you are looking at the graph of a function, can you construct a graph of the inverse just by looking at the graph? And this probably is something that you are familiar with. But on a graph, there's a cute way of looking at it so that if I give you the graph of a function, you can immediately tell me a graph of the inverse function. Something like, I'll just make a sort of straight line like that with a fairly shallow slope to it. Anybody seen this before? How can you give me a graph of the inverse function? Yeah?
You switch to x's and y values?
Right. So remember, the whole idea of the function versus its inverse is you are interchanging the inputs and the outputs, right? So the idea here is we sort of mirror, reflect all kind of x versus y values. Everything which used to be an x value becomes a y value. Everything which used to be a y value becomes an x value. If you think a little bit about exactly what that means in a picture like this, what that means is we can think of doing a reflection across this line, y equals x. If I do this kind of a diagonal mirror image across that line, this has the effect of swapping all of the role of x becomes y and the role of y becomes x. And so if that original thing is f of x, then the inverse in this example looks like that, right? This is f inverse, I'll write it as of x. But where that comes from is a mirror image of what I started with across this line. This is not confusing if I fill in too many things here, but If you think that's where the f of x used to be, and then I do this mirror image across the diagonal line, and I get the f inverse of x. All right, this is how you can see inverses on graphs. I hope that all of this, what I've said so far, is probably familiar to everybody. Any thoughts about all of that? One more thing which maybe you've seen, maybe you haven't. When it comes to doing calculus, there is similarly a trick for finding the derivative of an inverse of something. All right, there is a formula for that, which I would like to talk about. Derivative of the inverse. This is kind of cute, actually. It means there's a formula for the derivative of the inverse. Even if you are not able to find a formula for the inverse, like I said before, sometimes you just can't find a formula for the inverse. But even so, there is a formula for the derivative of the inverse, which you can always use. This is a little, I don't know, a little interesting in my opinion. There is a formula for the derivative of an inverse. And what it comes from is, it comes from part of the definition of an inverse is we know that f inverse of f of x is equal to x again, right? This is the definition of what it means to be the inverse, that when you plug one thing inside of its own inverse, you end up with x again. And this, we can take the derivative on both sides and use the chain rule. Take the derivative on both sides. And I will say in parentheses, use the chain rule. I mean, on the left side, we use the chain rule. On the right side, we're just going to get 1 when you take the derivative of x. But on the left side, since I have one thing inside of another thing, that's when you have to use the chain rule. So take the derivative on both sides. What we get, x here is just going to be 1. That's uninteresting. What do we get on the left side? The derivative of f inverse of f of x. Maybe I will just because I don't think we have ever used the chain rule yet this semester, this course, I mean, the derivative of g of f of x. That's what the chain rule is all about. Anyone remember this as a formula? Yeah?
Is it g prime f of x times f prime of x?
Yes, excellent. This is what the chain rule says. I don't know if I usually don't have this memorized in terms of a formula. The way that I remember this is I just remember you do the derivative of the outside function, you keep the same thing on the inside for now, and then separately you multiply times the derivative of the inside. This is the chain rule, all right? I wouldn't expect you to have this memorized as a formula, but I would expect you to know how to do this, those words that I just said. The derivative of g of f is the derivative of the outside with the same thing on the inside, and then times the derivative of the inside. And that is what I'm going to do right here. So when I do the derivative of this part, it becomes, so I'm just copying what's in the box, but instead of g, I'm calling it f inverse. And unfortunately, this looks a little ugly, but g itself is f inverse, and I have a g prime. So this is f inverse prime, that's g prime, right, of f of x times f prime of x, which is f prime of x. That's it. All right. And then we can solve this for f inverse prime in a somewhat weird way. So what I'm going to do at this point, we have a lot of kind of things inside of other things. Here's a little trick which will allow us to simplify this. I'm going to write x as the inverse of y, just for fun. Usually we write y equals f of x, but that's actually the same as writing this. This is just the same thing, but written the other way around. X equals f inverse of y. So I'm going to replace the x's with f inverse y's. It says f inverse prime of f inverse y. The reason I'm doing this slightly weird thing is because it's going to let us simplify things a little bit. Times f prime of f inverse y equals 1, right? I just substituted the x's for f inverse y's. Anybody see something that can be simplified here? There is actually part of this which we can simplify now. it's a little nasty looking right now, but it's going to get a little better. Yeah? Yeah?
Can you cross out the f of negative 1y with each other? Like in the parentheses?
Over here?
Yeah, with the other one.
No. It does have to do with this right here. Actually, you can simplify right here. Anybody see something? Yeah?
It's x. Yeah.
Oh, f inverse of y is x?
That's y.
Yeah, what I want to do is this whole thing right here is y. Because when you plug f inverse inside of f, they cancel out. That's the whole point of the inverse. All right? So f of f inverse y equals y. So this now says, f inverse prime of y times f prime, f inverse of y equals 1. All right? And then I'm going to just divide this thing onto the other side. It's a big multiplication in the middle, so we can just divide both sides by that thing sort of on the end of the left-hand side. And it says f inverse prime of y equals 1 over f prime f inverse of y. And this is a formula for the derivative of the inverse. Now, I'm using the variable called y, although usually this formula is written using the variable called x. So using x instead of y, I will put this, maybe I'll write this as a little, I'll write it as sort of a labeled theorem here. Would you mind if I write a theorem? This says, if f is differentiable, first of all, remember that just means that it has a derivative. Of course, if f doesn't have a derivative, then you shouldn't be talking about any of this stuff. But if I'm writing this as a theorem, I should tell you sort of what are the assumptions. If f is differentiable and 1-to-1, if you want to talk about the derivative of the inverse, first of all, there has to be a derivative, which is why it has to be differentiable, and also there has to be an inverse, which is why it has to be 1-to-1. But anyway, if f is differentiable and 1-to-1, then this is a formula about the derivative. It says the derivative of f inverse of x, which is exactly what I wrote here. It looks weird with the prime, the inverse, and then the prime. To me, it looks a little nicer if you write it this way. But it means the same thing. This is the derivative of f inverse of x. And it equals this, but I'm using the variable x instead of y. So it equals 1 over f prime f inverse of x. There you go. Strange but true formula for the derivative of the inverse of something. All right. This you may see from time to time. This might come up on the homework. Let's just do one example, and then I think we'll be done for today. But this you can, like I said, you can use this to find the derivative of the inverse even when you don't even know what the inverse is. So let's just try. How about f of x equals 2x plus cosine x. This is a function which is too weird to find the inverse function of. And if you look at it on a graph, looking at a graph is basically unhelpful. It looks like cosine does this kind of wave-like thing, but this is a function which it does this wave, but I'm also adding 2x everywhere. That means the wave, as it moves to the right, it also is going up, kind of like 2x. And it turns out that this is also going to be 1-to-1. So it looks kind of like this, something like that. You can graph it on your calculator if you're really interested, but it has this weird shape. The inverse function, what is the inverse function? I mean, as a graph, it has that, but it's mirrored across the y equals x line. Also unhelpful. But anyway, we can find, how about your job here is to find f inverse prime of 1. That's the derivative of f inverse, plugging in 1 for x. All right? We should be able to work this out, hopefully. We're just going to use the formula in the box, because that is exactly what the formula in the box is meant to tell us, the derivative of f inverse, when I plug in 1. So that just means the answer will be this, but with 1 plugged in, right? So f prime inverse, it's f inverse prime of 1 equals 1 over f prime of f inverse of 1, right? I took the formula in the box and I just used 1 instead of x. Sorry, you can't see it anymore. I took the formula in the box and just used 1 instead of x. Now, in order to actually say what the right-hand side of that is, we need to figure out what is f inverse of 1. This is a little tricky, perhaps. So what is... I'm trying to evaluate this fraction here. We better start sort of on the thing which is all the way on the inside of the parentheses. What is f inverse of 1? What that means is I want to find some x value where this function equals 1 as the answer, right? So we want 2x plus cosine of x equals 1, right? This is a hard thing to solve. I would say we kind of just have to try and guess the answer. Given you could try to solve this like using a computer or something, your equation solver on your calculator could do this. But can anyone say, given that I'm asking you to do this, you can probably just guess the answer? Anyone?
0.
0, yeah. If I'm telling you to guess the answer, it's probably 0 or 1 or something like that. It's 0 in this case. If you plug in x equals 0 on the left, you get 2 times 0 plus cosine of 0, which does equal 1. So it's x equals 0. This is just a guess. That step in general will be very hard to do, but I made the example so that you can actually do it. All right. So that means continuing that formula above. So f inverse prime of 1 equals 1 over f prime of 0. Right. That was that innermost part. Ended up equaling 0. Is there a way for us to find f prime of 0? I think there is, because I mean, this is f of x, right? So I think we can find f prime of 0 by taking the derivative of that. So what is f prime of 0? Remember, f of x equals 2x plus cosine x. And so if you ask me what is f prime of 0, we can find f prime of 0. That means take the derivative first and then plug in 0. So f prime of that, someone want to shout it out? What's the f prime of that? 2 minus sine of x. Great. So f prime of 0 is 2 minus sine of 0. Sine of 0 is 0, so it's just 2. All right? And so my final answer, you can plug in 2 to that fraction you see up top right now. So f inverse prime of 1 is 1/2. There you go. So we found the derivative of the inverse at this particular point, even though we don't even know what the inverse function is. Kind of cute, I would say. All right, that will do it.